theory for better or for worse. And then from there, then we'll get into like shortcuts and stuff like that. All right. So a hyperbola, I can give you a quick look at what a hyperbola would look like just in a, in a general sense. Here's a quick example of something that is hyperbolic after a fashion. It's got two distinct components, but it doesn't necessarily have to be oriented like this. All right. So that's just a quick view, but you can see it looks nothing like these equations. So we're looking at the conic section known as a hyperbola, and they always take on this form of x minus h squared minus y minus k squared, each over their own delta squared. Right, but the difference here is you can have two different variations of a hyperbola. Right, one of them is the case where it opens outward, and the other is the case where it opens upwards and downwards. Right, so I have to talk about the two different varieties here, just so you get an idea of what's going on. So what happens is, if we're working with the x minus h squared, I'm going to rewrite it here, x minus h squared over delta x squared plus y minus k, plus, geez Louise, minus y minus k squared over delta y squared is equal to 1. Right, so this is one variation of the hyperbola equation. The way this would manifest itself is that you would have some point hk that represents the center. All right. From that center, you would go left and right delta x units. All right. So you go delta x this way, you go delta x that way. Going to the left means that it's a negative movement. Going to the right means that it's a positive movement. Apparently I can't make a plus sign either, so let me fix that too. All right. At the end of this line segment, or at the end of these movements, you have your vertices. All right. Now, from our center, HK, you could also go up and down. All right. So let me resize this. Actually, I can't resize this. I'm just going to shift it over a little bit. You could also go up and down. That up and down movement is delta y. All right. So I'll do that in a different color. Going upward is a positive movement. Going downward is a negative movement. All right. This is the same concept so far as graphing an ellipse. In fact, if this had a plus sign in the middle here, then I would just make an oval around it and call it a day. But it doesn't, so we got to do something different. Right. So what we would get here is the four vertices that are relevant to a hyperbola. All right. Now, this is where things get kind of kooky. Right. As if it didn't always get kooky, but it's really going to get kooky here. There's really no way for me to make this smaller. All right, I'll just write it smaller. All right, so this is my, do it in green. HK. I'll even put it like right there. All right. I'm actually going to hang on to this anyway, because I'm going to need it again in a minute. I'll just tuck that over there. All right. So what we would do is create a rectangle surrounding these 4 points. All right. Creating a rectangle surrounding these 4 points would create what's known as an asymptote rectangle. So we just do that as a dashed line, a series of dashed lines, because these aren't actually part of the hyperbola. Right. What they do is they help us get boundaries, asymptotes for that hyperbola. All right. So we create a rectangle surrounding these points. Let me try to do that a little bit nicer. Close enough. And then let me make it dashed. At least the best I can anyway. All right. Now the four corners of this figure become relevant in the sense that if you connect an extended line through those 3 points, the 3 points that make up each corner and the center of the rectangle, you get the asymptotes for the hyperbola. Right? So it's going to look something like this. I'm just going to place it and then move it. I wanted to get it to kind of match up. But these are also going to be dashed because this is still not actually the hyperbola. This is going to give us the set of boundaries for that hyperbola. Okay, that looks terrible, but I can move it. Close. All right. So then you kind of look at this and say, all right, well, this is a heck of a diagram here. It's sort of a monstrosity. What's the purpose? What are we doing here? Well, at long last, what we can actually now do is graph this hyperbola. Now it's in general terms, so it's not gonna be overly specific because we don't have any numerical values, but I'll show you a case of that in a minute. All right, fixing that. But what we're gonna do for a hyperbola equation that's of this form is we're going to start with the rightmost vertex, draw a curve that approaches each asymptote as it extends outward, and then start with the leftmost vertex and draw a curve that approaches each asymptote as it goes outward. All right. We don't make use of this or this except to help us develop the shape of the figure. All right. But this pair of red curves, this is it's called a hyperbola. All right. So, and you can see that its structure is dictated almost exclusively based off of the same coordinates and relationships that you would see in an ellipse, right? So after all of this, that's the figure. The definition that we were looking to investigate here, transverse axis, that would be the line segment that connects the two vertices that are actually in physical contact with the hyperbola. All right. The conjugate axis is the line segment that's perpendicular to that. All right. So I kind of prematurely copied pasted. So I'm going to get rid of that. I'm going to take this and tweak it. Oh, not too much. Well, I guess I can still work with this. Get rid of the stuff that's not relevant here. All right. So I'm going to hang on to this for a sec. Now, that's one form of a hyperbola. I can give you a quick look at that. You know, if I plot just some equation, some hyperbola equation, let's say x minus 1 squared, just really anything that follows this structure. Let's say over 4 minus, let's say y plus 2 squared over 9 equals 1. All right, so it's got the same structure. It's opening outwards. But the line segment that would connect really the vertices that would be relevant, -1, -2. Let me just plot that here. This point and 3, -2. A line segment connecting those 2 points, that would be the transverse axis. All right. Now going the other way requires us to change the form of the equation. All right. So if I were to swap this around a little bit, so I have my standard form equation for this, that first variation of a hyperbola, but let's say I wanted to do it with the y information coming first. So a little switcherooski here. All right. Not much changes. You're still going to have a delta x that gives you the horizontal change from center. You're still going to have a delta y that gives you the vertical change from center. HK is still going to give you the center. It's just you're going to draw your curve now going upward from the highest vertex and downward from the lower vertex. So it's a vertically oriented hyperbola. All right. So in this context, the line segment that connects the 2 relevant vertices would be the vertical one. That would be my transverse axis. The one that's perpendicular to that would be my conjugate axis. All right. So a quick Desmos look at that. Let's say I just took the information that was in the first equation and I just swapped the x information with the y information. So I would have, well, let me do the fraction first. Y, I think it was y plus 2 squared over 9. Minus x minus 1 squared over 4. Whole thing equal to 1. All right. So I would turn this one off. But you can see here, hopefully, that it's an upward downward facing hyperbola. But if I actually activate both variations of this hyperbola, you would have 4 sets of vertices. Right? So 4 vertexes, really. So those 4 values would actually, if you were connected or connect them, make the corresponding ellipse, with the same parameters, with the center at 1, -2 in this instance, and the delta x value of 2, the delta y value of 3, it would create an ellipse. Right? So this is actually really creating graphs beyond the boundaries of an ellipse. Right? Because if I plot the vertices, it's really just the turning points along the graph. So I'm looking at really anything that would be symmetric about that center just living on these 2 hyperbolas, right? Now you see 4 curves here, but it's 2 hyperbolas. The black ones and the blue ones, they make up one graph, right? So this is a hyperbola. They're not hyperbolas, all right? So that's something to keep in mind, all right? But what I did somewhere along the lines in my Desmos investigations is I created a Desmos that has a hyperbola in general form. Now you can see it's just a mess here with all these points, but you'll eventually need all these points anyway. So if you know the center and the horizontal displacement, vertical displacement, it'll give you all the coordinates, it'll plot all the coordinates, it'll talk to you about the focus, which I'll get to in a minute. And then depending on what you need, you have a horizontal transverse axis versus if you have a vertical transverse axis, it'll give you the foci. All right. So there's a lot of good stuff that come from this, but it doesn't really mean too much at this point because you see all the craziness on the screen. Let's get into an example and I'll show you what that's all about. All right. There is a formula here for the distance from center to focus. It's the big denominator plus the little denominator. All right. In the previous lesson when we talked about ellipses, it was the big denominator minus the little denominator. And actually, when you add them, it doesn't matter what order you add them in, but for consistency, I have the big one coming first. All right. So yeah, it's another relationship that has to, I mean, I kind of bored you with that process last time. So I figured I'll just give it to you this time. But really, this is the distance from center to focus is the square root of those two denominators added together. All right. So as long as you do that, you'll know what the distance from center to focus is. So it's pretty easy. So yeah. You see the problem here, find the coordinates of the center, foci, and vertices if you know the standard form, which again, well, one variation of it is x minus h squared over delta x squared minus y minus k squared over delta y squared is equal to 1. Just kind of move this over. All right, so that's the model we're working off of here. So from that, I can see h and k are both 0, because otherwise it wouldn't have simplified down to just x squared and y squared on the top. So my center, this is a little thick. It's up to like, I like it at 0.65. All right, so the center, hk, is equal to 0, 0. My delta x is going to be equal to 5. That's my change from center. You say plus or minus 5, but as long as you know you're going left 5 and right 5, you're good. My delta y is going to be 4. That's the vertical displacement. So we have that information, which allows us to determine the vertices, right? So when we're graphing a hyperbola, if we're doing it by hand, since it's centered at 0, 0, I don't have to really worry about scaling too much, but 0, 0 would put me right there. If I'm going left and right 5 units, 1, 2, 3, 4, 5, that would put me here at negative 5, 0. If I go right 5, 2, 3, 4, 5, it'll put me over here at positive 5, 0. I'm going up 4 and down 4. So 0, 4, 0, negative 4. It's just if this were an ellipse, I would draw a smooth curve going through those points, but it's not. It's a hyperbola. All right. So I have my vertices. It's already plotted. If I label this on the graph, I will have accounted for 2 out of the 3 requirements, center, vertices, and in the process of creating the graph, I'll find the foci, so we'll be in good shape. But I'm going to create the asymptote rectangle, which is going to go through, I overshot the mark. It's going to go through the 4 vertices using only vertical and horizontal lines. All right, but it should be a dashed box. There's no way I can make that small. Okay, let me just do it this way. All right, so then I create my asymptotes. Not quite. Try that again. Make it dashed. Same thing. Going this away. You don't have to report the coordinates of the corners of the box. That's really not necessary. I mean, it's not relevant. That just gives us the boundaries for the hyperbola. All right. Now, since this is a hyperbola equation in which the x information comes first, this is one that'll open outwards. All right. It's a horizontally oriented hyperbola. All right. So that means that I'm plotting my curve through the rightmost and leftmost vertices. You know, as best you can, because that looks pretty crappy what I just did, but it's, you know, so far a full credit response. I mean, this one could be better in terms of its asymptotic relationship. All right. So then I just need to figure out the distance from center to focus. All right. So the proof behind it is kind of, it's kind of weird, but for now we're just going to go with the process. The distance from center to focus is going to be the square root. It's going to be the square root of the big denominator, 25, plus the little denominator, 16, right? So that gives me the square root of 41. That's a displacement value, all right? So what we do is we add that to and subtract it to the center, but only on the transverse axis. So a rule that we have here is the foci are always on the transverse axis. All right. So the transverse axis, that's why we needed to know that. The transverse axis is the axis that connects. I'm going to go with that pink color here. Connects the two relevant vertices. All right. So what this is telling me to do is go left radical 41 units and go right radical 41 units. So if I pop that into a calculator, square root of 41 would be about 6.4 units. All right. So I'm going to go right about 6.4 units. So 5, 6.4, left 6.4, right? This would be a focus. This would be a focus, all right? So I have a focus here at negative radical 41 comma 0, and a focus here at positive radical 41 comma 0. All right? You don't have to go with the decimal value if you don't want to. Right? That being said, you can at least get the decimal values from Desmos, because you'll see here the D distance from center to focus was about it was in the neighborhood of 6.4. Right. So 6.3, 6.4. So we're in pretty good shape there, but let me just kind of bring you back to scratch on this one here, just so you see what's going on. I'm going to turn off all these points real quick because it is kind of a jumbled mess so far. Just turning off all that. All right. So first things first, we have a center at 0, 0. So you still need to figure out this information here. All right, your center, your delta x, your delta y. All right, so I'm going to put my center at 0, 0. I'm going to put my a value, which is horizontal displacement from center, which is delta x. I'm going to make that a 5. Vertical displacement from center, that's my delta y. I'm going to make that a 4. So I have that information. So the coordinates of the center are plotted. The coordinates of the vertices, I still have the labels on. I just turned off the points so it didn't look like a jumbled mess. But you could see that those correspond. I mean, I could turn the points back on, but you see it kind of makes it moves things around and it makes things look a little nastier. So I'm going to just turn those off. But it's labeling the points relevant to the asymptote rectangle, the vertices. I get negative 5, 0, 5, 0, left and right, down and up, 0, negative 4, 0, positive 4. Right? Distance from center to focus, 6.4. Right? After I made the adjustment, I think before I said it was 6.3, but that was based off of the previous equation. So that wouldn't have been relevant here. But 6.4 is the displacement from center. Now, if you needed it as a radical, very easy to do. Just take, since I set it equal to d, take that d and square it. You know that it's radical this number, right? So that'll work. But bottom line is you now know how far you need to go in order to get to the foci. Now, I also have coordinates of the foci, select 1, because it depends on whether it's a horizontal transverse axis or a vertical transverse axis. All right, since it's a hyperbola that opens outward, it's a horizontal transverse axis. So I would tap on that one, and it would plot the points for me for the foci. But again, it's kind of messy, so you got to just sort of be careful. If anything, just kind of go into the neighborhood and zoom in a little bit so you can see what's going on, and then go into the other neighborhood, zoom in a little bit until you see what's going on. All right, but these points here, this one and this one, would make up the foci for this hyperbola. All right. So the information is there. It's just a matter of interpreting it and knowing, what goes where. Right. So that's one example with center at 0, 0. So for the check for attentiveness, I'm just going to ask you to take the notes for the second example. All right. You don't have to do the graph if you don't want to. So I'm going to just say here, I'll just draw a little line here. Check for attentiveness. If I can spell. I don't know why I capitalized the 4 here.
Do we have to write that down as well? Or, I mean, we're already doing this one, so you don't have to literally write check for attentiveness?
No.
Okay.
Yeah. No, it's the notes that matter. Yeah, I'm just indicating the problem that you need to write down. So name. Yeah, we've done this before. So anyway, it's everything that I write in this space here. Okay, so if we want to be literal, in this space here, that's going to get jotted down. Okay. And, you know, it kind of has to be this example because, hey, end of unit 3. So first things first, we need to know which model we're working with. Again, it's an equation where the x information comes first. So we're looking at a sideways oriented hyperbola. And that's because x information comes first in the equation. All right, which makes it a horizontal transverse axis. All right. So it's that situation. Now, people have told me in the past that the way they remembered this is if you actually put the transverse axis in here, you connect the 2 points, that little green line there would be the horizontal transverse axis. The figure almost looks like an H. H as in, if I made this a capital H in horizontal, the figure looks like an H, horizontal transverse axis. They said it helped. If it helps you, that's great. So I need that information because that's going to help me place my foci. And I'll know not to select vertical transverse axis. All right. So what I would then do is identify the center. All right. The center again is HK, which is going to be 3, 4. The delta X that's the horizontal displacement. I'm pretty sure, yeah, I knew it was going to move the shading on me. Horizontal displacement delta X is equal to 2. The vertical displacement delta Y is equal to 4. All right. So then before I even get to the graph, what I would do is compute the distance from center to focus. All right. So the distance from center to focus is going to be the square root of the sum of the 2 denominators. Big one first, little one second, just for consistency, but it doesn't really matter. 16 plus 4 gives you a rad 20. All right. So if I needed to come up with the information related to vertices without creating the graph, because sometimes it's just more convenient. Like you don't need to create the graph, but you need the information. All you'd have to do is take your X value, add it to and from, and subtract it from the X value of your center. So for your vertices, we would say 3 plus or minus 2, comma 4. All right, so you start with your center, add to it your delta X and subtract from it your delta X, but leave the Y alone. All right. Then for the vertical displacement values, we would start with the 3, leave that alone, then use the 4, the Y value of the center, add to it and subtract from it your vertical displacement. So I'd say 4 plus or minus 4. Those computations would give you the vertices without ever having to touch a piece of graph paper. All right. And the same idea would hold for the distance from center to focus. Since we know it's on a horizontal transverse axis, what I would do is I would take the center, I'm going to go red, 3, 4, add it to the x value and subtract it from the x value of that center. All right. So if I know that the displacement value is radical 20, I would do plus or minus rad 20 tacked on to the x value of the center. All right. So this is the center. Because it's a horizontal transverse axis, we tack it onto the x value of the center. All right. Now, all that being said, these numbers we can easily get from Desmos, but again, there's value in knowing the skill. So I know my h is 3. I can get it to lock it in. Come on. My k is 4. Horizontal displacement was only a 2, very small 2. My vertical displacement was a 4. I could leave that alone. So now it got messy. It got really messy. But if you zoom appropriately, just kind of go neighborhood by neighborhood, you get all the relevant pieces, right? So I have a focus value of about negative 1.472, a coordinate of a vertex at 1.4, 1 comma 4, right? That's what I would get in this computation if I did 3 minus 2. 3 minus 2 is 1, 1, 4, right? The other vertex, 5, 4, is what I would get if I did 3 plus 2, comma 4, right? 4 minus 4 is 0. So that's one vertex down. Oh, I don't know why I'm trying to circle that. That's one vertex down here. And then the 4 plus 4 gives you an 8, which is the other vertex up here. All right. So all the information that you need, including the vertices, they're all on this graph. It's just a matter of getting it on paper. All right. So as far as the check for attentiveness is concerned, I only need this. All right. What I'm about to write on the graph, you don't need to include that. Question?
Yeah, Professor, quick question.
Sure.
So on the test, would you ask, like, give us this and say find the center, find the vertex, find like all these different things, or like what type of question?
Yeah, so I could ask you to itemize it and say, I could say find the center and the vertices and the foci, but I could also say, give me the center, give me the horizontal displacement, the vertical displacement, and give me the distance from center to focus.
Okay.
So just certain aspects of it, rather than, because it's not practical to have people create entire graphs, just to answer a few questions. So I'll just kind of like cherry pick different things from it. But if you have these notes, this is like a good capsule summary of what I would be looking for. I wouldn't ask for all of these things. I would only ask for some of them.
Okay, thank you.
Okay. So then if I'm plotting points here, I just got to be mindful of scaling, because I mean, you're just looking on Desmos here. I gotta leave room to go up as high as 8 units up and 7 units to the right. So it's looking like I want to kind of offset this a little bit if I had to do it by hand, but this seems to be reasonable, kind of give it a little bit more room in the first quadrant. So plot 3, 4, 1, 2, 3, 4 is my center. I'm going left and right 2. I'm going up and down 4. Create my asymptote rectangle. When it's really small, it's kind of like, all right, I'm not going to use any line draw tools here. I'm just gonna kind of wing it. I mean, I could zoom in, but That's kind of overkill. All right. Then I create my asymptotes. That I'm going to do with the tool. They should be dashed also. And then we just want a smooth curve that's opening outward from the leftmost vertex. And the rightmost vertex. All right, then once I have that taken care of, I plot the foci and I'm good to go. So my foci are in the neighborhood of 7.5 on the right. Right, so now it's really a little bit more, between 4 and 5 units away from center. So I could plot it by the coordinates 7.5-ish, comma 4, from the x-axis, or I could just go from center, whatever my delta, my distance from center to focus is. So 1, 2, 3, 4, and change, that would be one focus value. And then 1, 2, 3, 4, and change, that would be another focus value. So one of them you'll call F1, and the other I'll call F2. All right. As long as you have the coordinates indicated somewhere, you're good. All right. So in the previous one, I indicated them on the graph. Here, I indicated them in my workspace, and then just kind of left the graph a little bare, I guess. But the mission was accomplished, and so we're good to go. Right?
You wouldn't want any radicals in the foci?
You could go either way with that. So I have a radical here, the radical 20. That's perfectly fine, or you can do some rounding, put it in decimal form and round it out.
Okay.
Yeah, either way is okay. Now, the only thing that I'd be remiss if I didn't mention this, but I don't think it warrants going over a unique problem just to get this point across. If this were reversed, so I'll just kind of jot it out real quick. If this were y minus 4 squared over 16 minus x minus 3 squared over 4 equals 1, the only thing that would change is that it would open upward and downward rather than outwards, which would cause the transverse axis to be vertical. And so this displacement here, this distance from center to focus, would be attached to the y value instead of the x value. All right, but every other aspect of the computations would remain the same. You'd still find the center the same way. You'd still find the horizontal displacement the same way, vertical displacement, the vertices. You'd still compute the distance from center to focus the same way. It's just that radical 20 would have got tacked onto the 4 instead of tacked onto the 3. And the curves would open upwards and downwards rather than outwards. All right. So like I said, I mean, it's such a minor adjustment that it's not even really worth getting into a unique example over. All right. So yeah. So that's really it. I'm going to stop the recording.